Great. So, hello. This is the first keynote that is going to be presented. My name is Stefanos Laskaridis again. And to introduce a bit myself, I have been in the distributed AI group of the Samsung AI Center in Cambridge for 3.5 years now. I did my MPhil in the University of Cambridge before that, and prior to that, I was at CERN in Switzerland. My research interests revolve around the areas of distributed and mobile systems, federated learning, and efficient deep learning to fit essentially deep neural networks on device. So today's talk is going to revolve around let's say four areas. We're going to start with like an introduction and the crash course to federated learning, federated learning 101, if you may. Then we're going to present the main challenges that are obstacles in deploying federated learning in the wild, the current state-of-the-art techniques that are tackling these challenges, as well as some open challenges and future directions for future research. So, Act 1, Intro to Federated Learning. So up until now, we have like the trend of deep neural networks becoming deeper, wider, and more accurate. A key enabler for this trend has been the hardware accelerators and the advancements in that field, such as the GPUs, FPGAs, ASICs, and so on and so forth, that have enabled training larger and more accurate deep neural networks in data centers. Of course, on-device training has only recently become a reality with the integration of powerful system on chips that integrate NPUs or mobile GPUs, and yeah, also the prioritization in terms of like strategics in the user privacy. So how is training handled today? So up until now, there is decentralized approach, where you have dedicated high-performance accelerators in centralized data centers. And also you have centralized data, so they are collocated. You have full control over the training process and mature tools to do that. However, you need to centralize all of your data, and this hurts the privacy of the users. And usually it is one model to fit all devices out there, and the cost the provider is bearing the cost. On the other hand, you have on-device training, where it's a more decentralized approach, and you can leverage the data on the devices without centralizing anything. However, you cannot really leverage external knowledge, and the tools and support for specialized hardware is not there yet. You have a device heterogeneity in terms of like different tiers of devices and generations of devices being out there. And of course, you have the restrictions from the standpoint of energy efficient and thermal behavior. So what is federated learning? What is all this fuss about? So federated learning, you start with a global model that resides on the server. You don't have any data there. And this global model is transferred to a sample of devices that are available. So these devices train locally on their local datasets, and they diverge towards these datasets, and they subsequently they send their gradients, so the updates that they have done on the model based on their local datasets, back to the server. And the server is doing an aggregation. This aggregation scheme might differ from system to system. So this would be the place that federated averaging would be, or you can use more advanced techniques such as FedProx, FedNova, or whatever. So what is really happening on each side? On the server side, you have the so-called outer loop, where you initialize the model, you sample the clients that are participating in one round, and then each client is getting the global model and it's doing the local training through the client update that you see here. The client update is like the normal training that you have been accustomed to up until now. So federated averaging is a basic aggregation scheme on the server side. It was initially proposed by McMahon and the rest of the Google team. And the optimization goal is to average essentially the loss functions, the losses that are coming from the clients that are participating during one round. And this is weighted by the number of examples that each client has. However, There are some downsides in federated averaging, namely that there is no server-side adaptivity. So you don't have a learning rate on the server side, and this is solved by FedAvg. All clients are doing the same amount of work, irrespective of whether they have more data or whether they are less or more compute capable. And last, it constitutes a naive averaging approach of the local gradients that can lead to insignificant global steps due to the different direction and magnitude of the update vectors. There are largely two deployment modes going on in federated learning, namely cross-device and cross-silo. So let's say broadly put, cross-device is massive deployments across devices out in the wild, where you have millions or potentially billions of devices, whereas the cross-silo setting is focused on the scenario that you have different entities that cannot exchange data straight directly, such as, for example, hospitals, and we're talking about like patients' data. So they need to collaborate for the same task, but without directly accessing each other's data. So the scale is very different between the two. The client participation is different. So usually you have sample devices on the cross-device setting because you cannot really broadcast a model in 1 million devices at the same time. Whereas in the case of cross-silo, you either have sampled or full participation. Then the data partitioning on the cross-device is essentially example-based. That means that each device has its own data set. Whereas in the cross-silo setting, you might not just have different, let's say, rows, different samples, but you might have different features residing in different entities. So that would be, for example, certain features are only known in one hospital and other features are known in another hospital for the same user. The primary bottleneck in cross-device setting has been communication, whether it's about the downstream communication, that means that taking the global model to the device, or in the case of cross-silo setting, it can be the computation and the communication. There is a lot of system heterogeneity in the cross-device setting. You have devices out there that vary tremendously in terms of their compute memory and network capabilities, whereas it's not that large of an issue in the cross-silo setting. In the cross-device setting, you don't address specific devices, and these devices are stateless. So you don't bear a state between two different runs. Actually, in the cross-device setting, you might only get to see a device once during training. Whereas in the cross-silo setting, that can be stateful. And then the reliability and availability is limited on the cross-device setting. So that means that you have failures or you have disconnections that are frequent, and you need to provision for these. Whereas in the cross-silo setting, this rate is low. Right. So up until now, I presented the vanilla variant of federated learning, but there are some different architectures that you might encounter in the literature. First one, it's the decentralized federated learning. So instead of having like a central single point of failure or bottleneck, you have a star and like organized in a star topology. You can have a peer-to-peer communication in a fully decentralized manner, and where each client performs the local updates and exchanges this information, the info with their neighbors. There is no global state, and the individual models need to reach consensus. But of course, the challenges are evident in terms of like the availability and reliability of the clients and the network, and the update frequency communication patterns of these entities. So another idea is the concept of hierarchical federated learning. So instead of aggregating to a single point, you might aggregate into entities that are in between the cloud server, let's say, and the clients. This can be, for example, some devices that are in your local network, such as the router, or it can be closer to the network ends up to the centralized server. And it offers scalability, variable privacy guarantees, as like the amount of trust that you put to each entity is going like from higher to lower, I guess. And you can take advantage of like the geographic locality in terms of like the data relevance that exists. So let's say some topics, for example, could be only relevant to a geographic cluster of devices, whereas it's not relevant in another. And last, we have the concept of split learning. So this is similar to offloading in inference settings, where you have a deep neural network split into 2 or more parts. And then you handle like one part on the mobile side, on the client side, and then the other one is handled by a more powerful device. So in this setting, you forward pass up to the split point, and then the server completes the computation. And then on the backward pass, the server backwards until the split point, then it moves the dependencies, it transfers the dependencies back to the client, and the client backpropagates to the head of the network. So in the figure here, the difference between A and B is the residence of the labels. So it's where the labels reside essentially. Yeah. And there is a work on the second work that you can see in the citation is on communication optimization for this split learning paradigm. So everything is nice. Now we know about what federated learning is, but where is it useful? So there have been use cases with Google being the first one in the game, with Google Keyboard and next word prediction, as well as Google Health Status. Next, we have Apple, where they have written a white paper about the personalization of their Siri system, ASR system, and you also have personalization of Apple News to its user. Then you have Facebook, or nowadays called Meta, on ad recommendation based on the actions of a user. You have the Alexa ASR. So this is speech recognition ASR. And last but not least, we have NVIDIA, and they did triaging of COVID-19 patients in terms of like the needs for supplemental oxygen with the NVIDIA Clara platform of theirs. So, all right, so we know where it fits, but let's say that we want to bootstrap. How do we do that? So there are a ton of frameworks and tool chains out there, and well, it's year more of them are coming out available to the users. These are all open source, and yeah, we have like frameworks from the big players such as Google. You have Facebook as well, Intel, IBM. You have we're going to use in this tutorial Flower, which is from the University of Cambridge and ADAP in Germany. And yeah, you can also see like systems such as FedML from the University of Southern California, FedScale from the University of Michigan, as well as PySift from Oxford. And the research datasets that have been used for benchmarking are, well, here we just divide them by the modality that they are referring to. So in terms of vision, you have CFAR 10 and 100, you have Feminist. This is the Federated Extended MNIST, Celeb, and then OpenImage and Google Landmark from Google, as well as the FedCV dataset from USC. NLP datasets include Shakespeare, Stack Overflow, and Reddit Corpora, as well as the FedNLP dataset collection. On the audio side, you have the Google Speech Commands and the Mozilla Common Voice. And last but not least, and most relevant to this tutorial, is going to be like the human activity recognition datasets. And we're going to use motion sense in our tutorial, but you also have like alternatives from different providers. All right, so yeah, everything is not that simple as I presented, because there are some challenges when it comes to deploying federated learning in the wild. And these challenges, well, they're by and large revolving around the area of data heterogeneity, the system heterogeneity, the bottlenecks of computation and communication, what happens in terms of privacy of the updates, that they cannot relate back to the raw data of the users, the availability of data, as well as the fairness and robustness of the system when it comes to adversarial actors, as well as you need to incentivize somehow the participants to offer their local resources as well as their data for the global good, let's say. Right. So let's go like more in depth into these challenges. So different clients, as I said before, have different dynamics. And these different dynamics come in the flavors of compute, memory, network bandwidth, or even the amount of data that they have. So if you have very slow devices next to really performant devices, then you have like inadvertently the existence of stragglers. And if you wait for these stragglers, then the whole system slows down. Otherwise, you might have like a deadline and then just not wait for the stragglers. But if you consistently drop the same devices or the same demographics of devices over time, then you're gonna introduce, first of all, unfairness and then some biasness in your model. And of course, the model itself might not fit in all of the devices in the first place. Also, you have limited availability and reliability of devices due to being battery powered, for instance, or like network disconnections, or even like task preemption because a user is using their devices and you prioritize the responsiveness of the device instead of just training something for global good. And last, you ask from users to commit their resources for global utility, as I said before. So you need some incentives to do so potentially. Right. On the client side, different clients have different data, and this is like generally called non-IID. So they're not independent or identically distributed the data. So different clients might be solving potentially slightly different tasks. Also, the client data can be temporally changing. So, for example, back in the day of, like, let's say 2018, you wouldn't have met the concept of COVID-19, right? Whereas nowadays it's like something that's very popular. So just by pressing some characters, you wouldn't have the recommendation for COVID-19. So this is an example of like temporally changing data. Of course, the data on the client side might not all be labeled for the supervised learning scenario, and you might be missing on a few or all the samples this data. And last, the updates cannot leak information at all about the raw data of the user. On the server side, you have partial participation in client selection. So, for example, not all clients are available all the time, and you also witness the diurnal pattern. So half of the planet is sleeping when the other is awake, and vice versa. The existence of malicious actors or compromised devices is a fact, especially in the wild deployments. So you need to account for that when you're deploying something in the wild. You have to decide on what you're going to do with delayed updates in the case of stragglers. So you might want to drop them, or you might want to integrate this with a discount factor. And last, you have, well, in big deployments at least, you need to account for the total communication volume over the one. So that means that you might have a non-negligible overhead to the network operator. So how to aggregate? Aggregation is not as straightforward as I said before in the case of federated averaging, because you might have some gray areas. In the case of batch normalization, for example, we have statistics, the mean and the standard deviation. You're normalizing the data that comes out of a layer width, and you also have some learnable beta and gamma parameters for linearly fitting that. So how you actually aggregate this in the global model is up for discussion, and you can, for example, estimate the mean and the standard deviation on demand by pinging some clients on the server, from the server side. Then also you might have optimizer state on the client side, and how this is married with the optimizer, the global optimizer state, is also up for discussion and up for design. And last, for having some privacy guarantees in the case of differential privacy and secure aggregation, you might need some number of clients and above in order to be able to offer that kind of guarantee. So how to aggregate securely? This is a segue for secure aggregation. So you might have, so when I said before that each client is sending their updates to a server, this server can be a trusted third party that you just blindly trust that they are going to do the aggregation and nothing more with your updates. So they're not going to try to do reverse engineer and lead back to your data. You might have approaches that are based on the trusted execution environments, such as the Intel SGX or the Trust Zone. And last but not least, you can enforce this trust via cryptographic techniques, such as the secure aggregation. So one quote I like from this paper from Peter at Google is that most researchers working in federated learning probably will not be deploying FL systems like at that scale. So yeah, at some point we'll need to also think about, okay, if it works in the millions, does it work on like the smaller scales as well? So the act 3 of the presentation is to show like what is the current state of the art and the landscape in federated learning. So on the data heterogeneity that I talked about before, you have different clients, different sized and distributions of data, and potentially with different feature and label distributions. So this is referred as non-IIDness, and it causes problems in terms of convergence. So you might want to bias your client selection. So instead of just uniformly and blindly picking your devices that are participating in a round, you might want to bias this towards clients that are offering more information towards your learning goal, so that is materialized by the loss magnitude, for instance. You might want to just accelerate the first steps of training through the device capability. So the most capable devices are prioritized in the first steps of learning, and then you gradually incorporate more low-tier devices. That is something that was done by ORT in OSDI. Yeah. Then you have a variable local update number of local steps and the reweighing of contribution, and this was done by FedProx and FedNova. You might want to incorporate some correction terms in your local optimization, and this is either for regularization or correcting the actual, bringing closer the updates and the task of global and local learning. And then you might model the whole process as a multitask learning procedure, and you want to treat different clients as solving slightly different tasks and adjust their losses based on the relatedness of these tasks. This was done by Virginia Smith, for instance. It's in here. Then we have the distributed optimization and aggregation, like kind of a field of work. Federated averaging has proven convergence under IID data, but not under non-IID data. And the convergence rates may struggle for that. And the question is like, how can different client tasks be married together to accelerate this convergence? You have adaptive federated optimizers. That was a paper from Reddy and al. And you have FedProx and FedNova, where you allow for partial client work contributions, and you have the introduction of like a proximal term in order to close the gap between the local updates and the global model. Then you have federated matched averaging, where, well, this accounts for the permutation invariance in neural networks, where you can flip. Essentially, the permutation invariance is like the order of neurons it doesn't really matter. So this work from Dimitris Papaliopoulos group was doing the aggregation in a layer-wise manner by matching the neurons or like the channels in terms of CNNs. You have scaffold from Pranith, Karim Reddy, and this corrects the client drift. So each client is training on their local dataset, and the task might drift apart from like the global goal. So the authors there are introducing a control variant in order to control like the local updates. And from the same authors, you have mine as well, that is synchronizing the local optimizer state. On system heterogeneity, you have devices that have vastly different compute, memory, and bandwidth capabilities. And this can lead to either stragglers hindering the convergence rates or dropout of slow clients, leading to biasness and unfairness. So you can reduce the model and update size with different techniques from the literature, either through pruning or dropout. So that means that you're not using some of the neurons in the neural network. Through quantization, so you drop the precision of the calculations that are happening, and this leads to gains in compute, because if you have like if the operations are done in a manner in kernels that are taking advantage of the lower precision, and you have upstream and downstream communication gains as well as memory residence. You have the sparsification of the updates, where you essentially sparsify the gradients, and you don't need to send that much information, factorization, and also architectural changes. lots of work in that domain. We have actually contributed that domain through Fjord accelerated NeurIPS, but I'm not going to go through the details for that. Also, you have different techniques such as accepting asynchronous updates. For example, Papaya was this work from Meta that was avoiding stragglers by not having strict synchronization barriers when doing the averaging, and you allow with some discount factor to get the stale updates. And last, you have the offloading via split learning that I talked about before. So another big field in the area of federated learning is personalization. This is like there is an inherent tension, as I said before, between like having a globally good model and what is personally good for the client at hand. So this affects the magnitude and the direction of steps during optimization. So you have a family of techniques that are taking advantage of like meta learning in order to learn a good initial state that is a global model that can be personalized quickly locally by the clients. Then you have approaches that are splitting the model, the global model, into something that is globally shared aggregated across clients, and then you have fine-tunable parts that are not shared globally to other entities. And last but not least, you can combine these personalized and global models and either alternate between them or combine these two in order to regularize the updates to the global model. Yeah, as I said before, the existence of labels is something that cannot be taken for granted in the area of federated learning. So in the wild, you might have data that are not annotated. And this unavailability of labels might be due to the use case that you point. It might be due to the cost of annotation itself, and you cannot ask from the users to do it, or even like the need for expert knowledge that the user is not in that set of experts. So you have techniques on the from the semi-supervised learning domain as well as the unsupervised domain, where you can learn from partially annotated data in the first place that can reside on the server on the client side. And typically, you have regularization through enforcing consistency between different perturbation of the same data, or even across clients. And yeah, last, it's like there is one work on unsupervised federated learning that is using surrogate data and it's training in a surrogate model, and then they do the knowledge recovery in order to apply these updates to the actual model. On the privacy updates, yeah, naively sending gradients from the clients to the server leaks information about the dataset. This has been proven, and yeah, you have two main techniques, namely secure aggregation and differential privacy. In the case of secure aggregation, well, the server does not need to know the specific updates from each client, but it just needs to know the total aggregate of these updates. So by using secure multi-party computation, you can get around this. And next, you have differential privacy approaches where you essentially add some noise to the updates. You can add this noise to different parts of the process, such as like this centrally on the server or locally on the client side before sending upstream. But just doing this naively will lead to poor performance. So yeah. Last, I want to talk about like the robustness and privacy of the federated learning system. So on the one hand, you need to be able to have a system that is robust to Byzantine failures, and also you want the potentially like from the provider's perspective not to leak the proprietary global model as a whole to the client. Yes, so there are different works in each domain. The first one is it's distinguishing between like the data poisoning attacks in terms of like the data manipulation. So you're manipulating the data, but the model stays as it is, whereas there are other techniques that are just altering the gradients themselves before sending them to the global model. And of course, there is some work on the, let's say that you have been poisoned already. So that means that your clients are already compromised, and how do you mitigate this this impact? And Waffle is work on leakage of the proprietary global model. All right, and last, I'm going to talk about some open challenges and future directions in the area of federated learning. So, as aforementioned, the interaction between privacy, communication, and computation, accuracy, and sparsity in the area is it leads to like a tricky balance, as well as like having the system robustness and fairness in during operation. So like finding this balance point across different systems is non-trivial, and of course there is a lot of research to be done in that domain. You have also the behavior of federated learning systems under continual learning operations. So so up until now, you have seen systems that are trained in an episodic manner. That means that they're trained in snapshots. You train, you deploy, and then you train something different, and then you just deploy in the next update of the clients or the application or like the whole operating system. However, you might see now systems that are deployed like in a continual fashion, and you might come across problems such as distribution shifts, temporal shifts in the data, not just non-IIDness. That means that it's the difference between the clients, but also like all clients are drifting their topics, for instance, towards something different, as well as like catastrophic forgetting, of course. Yeah, then we have to balance out the global knowledge and the global goal with respect to like the personal goal of each client. That's not solved yet, and there is it's an active field of research. You have techniques that are either manually or automatically designing the model itself in order to adjust to the capabilities of the clients and treat essentially the system heterogeneity. So you might come across neural architecture search techniques, for example, that tune the model architecture to account for the client capabilities in a hardware-aware manner. Then you have techniques that are selecting clients in a biased manner in order to accelerate convergence. But the balance between the convergence and the fairness is also up for discussion and not solved in any case. And last, you might have alternative participation schemes. So up until now, the rule is that normally clients will, let's say, in the cross-device setting where you have smartphones, they are usually participating when they are plugged in and connected to an unmetered connection. However, there might be use cases that you need opportunistic device participation, and this changes the dynamics of the whole learning process and the availability of the clients as well. So that was pretty much what I had to say. I'm open for questions. And before we move to the Q&A, some announcements is that we're hiring for interns and full-time positions in federated learning at Samsung in Cambridge. And we're also organizing the embedded and mobile deep learning workshop at Mobusys 2022. So we're looking forward to your submissions and actually seeing you there in Oregon. Thanks a lot.